The most difficult workload in language agents today is autonomous long-form deep research. The goal here is not a simple question and answer extraction. The objective is to produce a comprehensive report synthesized from thousands of raw sources. This requires a multifaceted investigation spanning an extended time horizon. An agent must hold on to a central thesis while exploring dozens of tangential data points over hundreds of discrete steps. The standard architecture the industry relies on to attempt this is the single-agent react loop, an iterative cycle of think, act, and observe. The react loop excels at short, linear reasoning tasks, but when applied to deep research, the architecture structurally breaks. The standard react loop linearly appends every action and observation to a single growing trajectory. This accumulation creates extreme context dilution, burying salient information. Furthermore, execution remains entirely synchronous. Any minor subtask halts the forward progression of the entire global trajectory until it resolves. To bypass this, developers generally reach for one of two architectural patches. The first is summarization, where an external model compresses the context prefix once it nears the token limit. But summarization is a form of lossy compression. Selecting exactly which data points will matter 50 steps later is nearly impossible, resulting in severe information loss. The second patch is context folding at subtask boundaries, popularized by frameworks like FoldAgent. This reduces token load, but it still forces the agent to execute tasks sequentially inside a shared context window. Patching the context window does not solve the root issue. The underlying problem is that the single-agent architecture lacks proper concurrency primitives. Researchers recently published a new architecture called Self-Manager, which addresses this by rebuilding the single agent using thread structures borrowed directly from operating systems. They split the global React trajectory, upgraded to act exclusively as a main thread orchestrator. It can dynamically spawn multiple independent subthreads. This introduces context isolation. Subthreads execute their own React loops in dedicated windows. Raw search histories never pollute the main thread. They return only a synthesized, compact result. This enables true asynchrony. The main thread is never blocked by a running subtask. The only time the main thread pauses is when it is directly querying the base LLM. It also enables concurrency. The main thread can initialize multiple separate subtasks simultaneously in a single iteration turn, allowing it to explore different facets of a research problem simultaneously. This creates a structural tension. If context is strictly isolated, how does the main thread track what its subthreads are actually doing without bloating its own context window? Solving this visibility problem is what turns a parallel agent into a self-managing agent. The solution is the Thread Control Block, or TCB. This is another concept lifted directly from OS design. An OS TCB manages low-level pointers, but the Self-Manager TCB is a lightweight metadata envelope. It contains specific fields: thread ID, goal, state, allowed tools, context, and result. The critical field is state, continually tracking if a subthread is running, successful, failed, or killed. At every single turn, a clean list of these current TCBs is injected directly into the main thread's observe face. This real-time observation expands the main thread's action space. The orchestrator executes a branch command to create threads for uncovered topics. It can send a kill command to terminate threads running too long, or delete to clear old TCBs and free up computational attention. If the main thread simply needs to wait for subthreads to return their data, it can explicitly execute a sleep command. The TCBs provide complete orchestration oversight while keeping the main thread's context window perfectly pristine. To see how this behaves in practice, we can look at an execution vignette from the paper's experiments. Here, the main thread is monitoring 3 active subthreads. The main thread determines it needs granular data on a specific facet of the global problem, so it branches a new subtask. That subthread begins asynchronously executing web queries in complete isolation. Meanwhile, the main thread continues its own synthesis. It observes the updated TCB list and realizes that specific subthread's goal is no longer relevant to the evolving global task. Instead of waiting for the subthread to finish, the main thread immediately executes an early stopping kill command. This creates an immediate hardware efficiency. 0 computational resources are wasted executing a dead-end task. This active, real-time pruning transforms a rigid sequential sequence into highly adaptive orchestration. This is the literal definition of a self-manager. The empirical data proves that this architecture directly solves the context dilution problem. This chart displays the information loss rate, a metric tracking how much data is dropped at context transitions. Self-manager operates with an 11.53% loss rate, compared to the resum summarization approach, which loses 25.23% of its information. Strict context isolation cuts information loss in half compared to standard summarization techniques. Because the main thread is shielded from raw search data, it maintains a much smaller overall context length, allowing it to sustain significantly longer time horizon planning. We can see the result of this in the Deep Research Bench, an evaluation suite of 100 complex long-form tasks graded by an LLM as judge. Looking at the Deep Research Bench leaderboard, Self-Manager running on a 30 billion parameter model scores a 44.33. This outperforms all single-agent baselines and surpasses complex multi-agent workflow-based systems. Superior context management directly yields superior long-horizon reasoning. Moving to the economic realities, total token costs do rise slightly due to increased tool usage, but wall clock execution time drops. The baseline architecture executes in 129 seconds. If asynchrony is artificially disabled, that same task balloons to 193 seconds. Modern inference frameworks like SGLang support this concurrent multithreading natively, executing the parallel calls without adding inference overhead. Despite spawning multiple threads, this is strictly not a multi-agent system. All threads share a single, iteratively composable policy. There are no predefined, hard-coded workflows connecting disparate models. By fixing concurrency primitives at the OS level, a single-agent architecture can finally generalize to arbitrary deep research tasks without drowning in its own context.